Hi everyone, welcome to our video on sketching a curve using our rules for the first derivative and the second derivative. So the curve sketching problem, if we're doing it purely by hand, is like combining our increasing, decreasing, and relative max problems with the concavity problems. So we would use the first derivative to tell us about, go ahead and just make it kind of a tree here. Our first derivative tells us where it's increasing and decreasing. It also tells us where you have relative extrema. And these two are connected. And then our second derivative tells us about concavity and inflection points. Okay, and those two are connected. All right, so it is combining those long problems. If you have been going in order of my videos, let me not even scroll, just those first derivative problems and the second derivative problems in one. Now, we also can use a calculator to help us, and that would be fast. Now, it might not give us exact values, though, so that's the one problem. All right, but it really does help with these first three. So this is just using rules for pre-calc. And so let's go ahead. I'm going to start with the calculator. So we'll get our picture going. Okay, so and then I want to come back to the rules. So on this problem, it just says graph the following. And then we have this one function. So the x to the 4. So we've got x to the 4 minus 16x squared. And then it looks like it goes down pretty far. Let's go ahead and change our x-axis. So let's just go to about -8. And let's do +8. And then that way it's a little better. Let's also change our y. Okay, so our y, it looks like it went pretty far down. So let's go to -60. And that's probably fine. And +60. And then there we go. Let me scroll. So there we go. So we can see it all. Notice the scale. The x-axis is going by 1s. Our y-axis looks like it's going by 5s. Okay, so that's to put it in to see it all. Okay, so this does tell us everything. So there's our x-intercepts. Right there. Any x point that's on the x-axis is a x-intercept. All right, we also have our one y-intercept is the one point that's on the y-axis, so it is shared with the x-intercept. Even with this, we can see it looks like here's where we have a relative minimum, and here's where we have a relative minimum, and then at 0, 0, we do have a relative maximum. So we get a lot of information just by graphing it. We can see the type of concavity. It looks like it's concave up at first. Somewhere it changes, though. So that's where the second derivative test can help us be more accurate. So I would say it's somewhere around here is where it changes from concave up to concave down. Because here we have the cup, concave up like a cup, and then concave down here, it's definitely looking like a frown. Okay, and then it's back to concave up. Okay, so this tells us a lot of the information very quickly. All right, but let's go ahead and break down this scenario. So we'll come back to this sketch. But let's assume they want more accurate values than some of the decimals they got. All right, so let's identify. So the pre-calc stuff, I'm going to number it the same way. So step 1 in this problem, the domain. Well, this is a polynomial, so it goes back to domain rules. So if it's a different type of function, we have different rules for it. With this is just a polynomial. And so the domain of a polynomial is always -infinity to +infinity. And that's it. Moving on. Step 2. Step 2 is find the intercepts. So I want to find, let's do the y-intercept first. So we already saw it on the graph, but this is a good reminder for other problems. So the y-intercept is to let x equal 0. So that means we'll just use our function here and plug 0 in for the x's. So that means it's f of 0 equals 0 to the 4 minus 16 times 0 squared. That would be 0. And so when x is 0, y is 0. So that's our y-intercept. And there's at most there's one y-intercept. So it's either 1 or 0 y-intercepts. And then the x-intercept, though, could have more. Oops, this is still number 2 x-intercepts. And we saw it already on the graph. But again, there's good practice. To find the x-intercepts, we let y equal 0, which means you set your whole function really equal to 0. So this is the same as, let's put it in parentheses, this is, or set your whole function equal to 0. So remember, y is f of x, so those are the same. So if I set the whole left side equal to 0, I'm going to have, let's put it over here. So I have 0 equals x to the 4 minus 16x squared. And then to do these types of problems, we would factor. So we would get x squared is in common. And we'd have x squared minus 16. And then I can continue factoring. That's x squared times x minus 4 and x plus 4. And so taking each of these and setting them equal to 0, x squared is 0, x minus 4 is 0, and x plus 4 is 0. We get our 3 answers here. So x equals 0 is one of them. Add 4 over, x is 4 is another. Subtract 4, x is negative 4 is the last. Okay, so what we have here, again, that's when our y was 0. We got these x values. So that means we have, I'm going to put them in order. So the smallest one is negative 4, and the y coordinate was 0. And then we have an x coordinate of 0. Y coordinate was 0. And then we have the x coordinate of 4. Y coordinate also is still 0. Okay, so these are the x-intercepts. So the y coordinate is 0 on them. Okay, and with that, that means you could, at any moment, you could start graphing. So for instance, let's go ahead and get these points just plotted. Okay, so the x-axis, 1, 2, 3, negative 4 is there. Here's 0, 0. And then 1, 2, 3, 4 is here. All right, so there's those 3 points. Step 3, well, again, our picture of the graph did not show any vertical or horizontal asymptotes. Those are for other types of functions. So our vertical or horizontal asymptotes. And that's why it's nice to graph it first. You could visually see them immediately in the problems if you do graph it first. But these occur with rational functions, rational, log, or exponential. Okay, so let me spell exponential, right? Okay, so exponential. Okay, so and we don't have that in this problem, so that means we don't have any. So we'll move on to the next part. Okay, and the next part is the first derivative test. Okay, so number 4, I'm just going to label it first derivative. All right, well, let's take our function and find its derivative. So that's f prime of x would be 4x cubed minus 32x. And then, like always, we would want to factor it. So we have f prime of x is 4x is in common with 4 and 32x. 4x cubed and 32x, I mean. So that's what's in common. And then we would be left with an x squared minus 8. And then you could distribute and double check, yes, this is correct. And then once we check that, now we can set each factor equal to 0. So 4x equals 0 and x squared minus 8 equals 0. And then we usually cloud it. So let me actually go back and just say, hey, this is going to be important for us. We use this in multiple parts. And then, well, we could solve each of these. If I divide the first one by 4, that one is instantly solved. Its x is 0. With this one, I could add 8 over. So we'd have x squared equals 8. And then we would square root both sides. When we square root, remember we would use plus minus. Square root of 8 is, okay, so is the square root of 8. Plus minus square root of 8. However, they might want us to simplify that. The square root of 8 is the same thing as 4 times 2. Like that. So square root of 8 is the square root of 4 times the square root of 2. But the square root of 4 we could do. So that is 2, and then times square root of 2. Okay, so this was just scratch work, so it's 2 root 2. So this is the same thing as negative 2 root 2 and positive 2 root 2. So I'm just separating the plus and minus at the same time. There we go. Okay, so these are our critical numbers. And once we have our critical numbers, that's where we would start to use a number line. Okay, so let's use, I'm going to do it right here to the side. Let's set our number line up. So we have negative 2 root 2 is the negative one, 0, and then positive 2 root 2. So those are our three critical numbers. This is our x, and then what I want is my f prime info, and then I'll have my f info. And this is where we use values in between these to help us with figuring out what the sign is with f prime. Okay, so I'm going to choose something larger than 2 root 2. Well, this number I don't know exactly, so I'm going to play it safe and just use 100. I know for sure f prime of, I know 100 is bigger than 2 root 2. And at this point too, you could again use a calculator and verify the decimals with our graph that we already graphed. But let's go ahead and continue breaking it down without referencing it. All right, so if I plug in 100 into our derivative, 4 times 100 would be 400. And then 100 squared is a large number minus 8. That's just going to be positive. I'm just going to write plus. So 400 times a positive value is positive. Remember, all we care about is the sign, so we don't need to actually calculate it all the way. All right, and then in between 0 and 2 radical 2. Well, again, without even using a calculator, I know 1 is less than 2 radical 2, because 2 times something radical 2 is going to be bigger. All right, anyway, so you could always check again. But if I do plug this in right here, I'd have a positive 4 times 1 minus 8 would be negative 7. And then this is negative. Positive 4 times a negative 7 is negative. And then let's keep going. F prime of negative 1. Plugging that into our function over here. Let me just go ahead and start. That's what I'm plugging it into. I would have 4 times negative 1 is negative 4. And then negative 1 squared is 1. Minus 8 is negative 7. So negative 4 times negative 7, that is positive. And then one last time, f prime of negative 100. So I know for sure that's left of negative 2 radical 2. So if I plug negative 100 in, I would have negative 400. And then negative 100 squared is a positive number. Minus 8 will stay positive. So negative 400 times a positive number would be negative. And then now I know what f's going to do. So where f prime is negative, f is decreasing. Where f prime is positive, f is increasing. There we go. So those are the intervals of importance to us. Okay, and then now I could still also find, let's go ahead and get those marked on here. So it looks like I have my relative minimum. So because it goes down and then up. At this x-coordinate, I have a relative max at this coordinate, and then I have a relative minimum at this coordinate of x. And so let's get those. So we would plug those into our function at this point. So we've got f of negative 2 radical 2, so this is where this one, so remember these two, let me put it right here next to it, the plus minus. These two are the same. So it's usually easier at this point to actually use just the square root of 8. So in math, they usually like you to simplify, and I think that's loosely in quotes simplifying, because this is easier to work with. Okay, so if we were to plug this into our original function, so the x to the 4 minus 16x squared, we would have negative radical 8 to the 4 minus 16 times negative radical 8 squared. And then what's going to happen with this? Well, this is the square root of 8 times the square root of 8 times square root of 8 times square root of 8, which really is just 8 times 8. It would be 64. Minus, this becomes 16 times 8. Well, 16 times 8, I could use a calculator. I'm just going to use this over here, my scratch work. is, so 48 and then 128. So it is minus 128 like that. And then what this becomes is negative 64. Okay, so it looks like I have the point of, let me put it, I'm going to squeeze it in right here and box it, negative 2 radical 2, comma, negative 64. So that's where a minimum occurs. When I plug 0 in, we would get 0, because 0 to the 4 minus 16 times 0 would be 0. And we already had that point already anyway from above. It's right there. Okay, so I didn't have to do much, but this is where a relative max occurs. So I'm going to go ahead and highlight it. So that's listing it as a point instead of saying it in words. So there's a relative min. And then one other relative minimum occurs at positive 2 radical 2. Well, without doing the work, it is going to match what we did for this first one. It will be negative 64. And so I'm just going to write it. And again, we'll check in our calculator anyway. But there it is. That is another point where a relative minimum occurs. Okay, so there's the first derivative test. And even at this point, we could plot those values. We would need to estimate the square root of 8. So the square root of 8 is close to the square root of 9, which is 3. So it's a little smaller than 3. So 1, 2, 3. So this is about 3, and then down 64. Well, my grid is not matching that. We'll say each of these is about 5, 10, 15, so forth. Okay, and then that way it's at least to some scale. Okay, so we're at very close to 3, but not exactly 3, and then I need to go down 64. Okay, so 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Actually, 5 is not a good scale. Sorry about that, because it would have been off anyway. Okay, so let's go every 8. 8, 16, 24. Sorry about that. And then 32, 40, 48, 56, and then finally 64. So it should be about here, and there's 1, 2, 3, a little less than 3, about there. And then similar with the other side, 1, 2, about 3 to the left, and there we go. Okay, so that's where those points are. And then 0, 0 is already marked. Let me mark those with my numbers and my points. Okay, and this one was negative 2 radical 2, negative 64. This one was positive 2 radical 2, not positive, negative 64 still. Okay, so those are those points. So it's coming together, which again we have on our calculator already, which we could double check. Okay, but this was getting those x coordinates as exact values at least. All right, and then now number 5. So we're going to squeeze that in here. That's our second derivative stuff. All right, so I'm going to using this one. I don't really mark it. I guess I'll put it in a very small star. With this one, this is easier to take the second derivative. So let me rewrite the first derivative down right here. Oops, 32 minus 32x, like that. Okay, and then now let's take the second derivative. So the second derivative is 12x squared minus 32. And then looking at this, it looks like a 4 could be factored out. But at this point, since there's not much reason to just factor out a constant, I'm just going to circle it with my cloud, or cloud it. And then now let's set it equal to 0 and start to solve. Okay, so if I have 0 equals 12x squared minus 32, I can add the 32 over. So 32 equals 12x squared. I could divide by 12, and then that would give me, well, let me show the 12. So dividing each of those by 12. 32 divided by 12, that can be reduced. they are each divisible by 4, so it would be 8/3 is x squared. And then now I can square root both sides to get my x. And remember, plus minus on the constant portion. Okay, so I've got x is equal to the plus minus. Now, the square root of 8/3 is the same as the square root of 8 over the square root of 3. And then we saw the square root of 8 was, so let's write the plus minus 2 root 2 over the square root of 3, like that. And then I'm just thinking, like, worst case scenario, if they want you to rationalize this, we would multiply both top and bottom by the square root of 3. And then so that way we have our critical numbers. X is equal to, let's separate them, the negative. So 2, root 2 and root 3 would become root 6. Root 3 and root 3 would become just 3. And that was the negative, and then we also have the positive of it. Okay, so that's if they want you to simplify and use radicals instead of decimals. So these are the critical numbers for our second derivative. And then now that we have these critical numbers, let's go ahead and set up our number line. So we have the negative 2 radical 6 over 3, and we have the 2 radical 6 over 3. All right, and then now I'm going to use purple for our second derivative stuff, which is looking at this function. And there's my f. Here's my x coordinates. All right, and then, well, it's just plug in something in between these intervals to test the sign of the second derivative. So let's do f double prime. So anything bigger than this number, I don't know what this number is immediately, but I know 100 is going to be bigger than it. Okay, because this is some small fraction, it looks like. And so if I plug 100 into our second derivative, I would have 12 times 100 squared is a large positive number, minus 32 is going to stay positive. When I plug 0 in, so that's in between these two. When I plug 0 into my second derivative, it looks like I'd have just negative 32 left over, and that's negative. And then one more time, if I plug in negative 100, I know that that's definitely left of this value. Negative 100 squared is positive, times 12 is a large positive number, minus 32 would stay positive. Okay, and then now that I've done this number line, I also think, hey, whenever I have the second derivative, I've got my two friends to help me out, where these are the signs of our second derivative, and then this tells us about the concavity. Okay, so where it's positive is where it's concave up. There we go. And where it's negative is where it's concave down. Right there. Okay, and so I don't have enough room to show the inflection point, but I will use the calculator to help me finish this off. Okay, so we do have everything. Now let's verify. So we already saw the graph. Boom. There it is. It looks like a W. So I know those connect like this. And everything does match with our number line. So for instance, it does decrease, it does increase, it does decrease, and then it does increase. So everything's matched, and then the concavity will match as well. So that's more important. So all of this here we could have used to get our sketch before plugging it into the calculator. So we're kind of doing it in reverse, but that's okay. Okay, so let's show this. So it does do something, and mine might be perfect because it's a little hard to draw with my computer pen. So I'm going to try my best. Oh, let me try that again. I could do better. Okay, so I'm just trying to connect the dots. Ooh, that's okay. And then up, and then down. There we go. Not the best, not the worst. Oh boy. Okay, that's as good as I'm going to do. Okay, so we have all these important points, and those are our intercepts. Let's go ahead and label those as well. All right, and so what I wanted to do was get our inflection points. Notice our graph is met, so our intercepts we have. Let's verify that I do have those minimums correct. Okay, so I'm using the radical form. So let's make sure the negative, so I'm going to write the point, negative 2 square root 2, and then comma, negative 64, and then, yeah, good. So you can see that dot popped up. Yep, awesome. Okay, so that's where the minimum was, and then also this same thing, but it was positive. So I'm just copy and paste, and good. So we can see that. So we do have a match. Okay, so that's great. That's great news. Okay, so those two are the same. All right, so we got them. All right, and then now I want to plug in what I have for the inflection x coordinate. All right, so that negative 2 root 6 over 3. Well, I'm going to use the table for that. Oops. Done. Yeah, let me go to convert to table. Yeah, that's what I want. Okay, so let me plug in the negative 2 square root. Ooh, will it let me? There it goes. Square root of 6, and then divided by 3. There it is. There it is right there. And then we could do the positive one of it. So we have 2 square root of 6 divided by 3. And there it is. And that certainly looks where the concavity changes. So concave down, inflection point, and now it's concave up, inflection point. Okay, and I don't know why I plotted that. I think it's just because I probably clicked on it. Okay, so that's not super important, but whatever. Okay, so we've got those, and same deal with that too. I think it's just because those are still in here. Okay, so let me see if I can just delete them. There we go. Okay, so those were not really important to us. Okay, so but those are where the inflection points are right there. Okay, and if I really needed to find exact values for those, okay, so here I have them as decimals. Well, I could really plug them all into my equation here to really make sure I've got it. So one last thing, I'm going to do the scientific one. And then all I'm going to do is plug in the 2 square root 6 divided by 3 to the 4th power minus 16, and then 2 square root 6 divided by, oops, not yet, divided by 3 squared. And that's what the decimal was in the calculator. So well, it looks good. It looks like we got it. Enter. And if we really needed to, I guess we could do it to the 4th power. Let's see if it changes it to a fraction. There it goes. Nice. Okay, so negative 320 over 9 is what that would have became. Okay, so now let me plot that. Okay, so the 2, they're about here, we'll say, and about here. Okay, so that point, let me go ahead and just put it in purple and just mark it to the side. So that was our negative 2 root 6 over 3, comma, negative 320 over 9. This one in the purple was the positive one of it. Okay, so I'm probably going to run out of room on it. Let me squeeze it in. Negative 320 over 9. Okay, so there it is. Okay, so very long problem when we use calculus. This was a lot more important. This was much more important years ago without calculators. Okay, so it would have taken a long time, but we would have gotten this graph very accurate with our tools of calculus. All right, so whatever method you take, it's still good to know how to do the derivatives. It's still good practice. It's still a lot of things that are used in other stuff in other parts of math. So I mean, try these by hand. Make sure you can do them. But certainly also do it with the calculator to help yourself out to make sure you are getting it right. All right, so that's it. Thank you for watching, and I will see you next time.